In 2.2a, we're going to look at the normal distribution and look at what falls within the interval of 1, 2, and 3 standard deviations of the mean, which is referred to as the 68, 95, 99.7 rule. So let's first start off by defining what a normal curve is. A normal curve is a class of density curves that have the same overall shape. They are symmetric, single-peaked, and bell-shaped. So down here to the right, this is a normal curve. We're going to be using these pretty much again to the end of the entire book. Now, a normal distribution, therefore, is a distribution of normal-shaped curves. And sometimes you will see an abbreviation used where it's in a parentheses format like an ordered pair. The capital N means it's a normal distribution. And then the first value they're going to list is actually going to be the mean, and the second is the standard deviation. So if you ever see this notation here, you can read it accordingly. Now here is a standard normal curve. What you're going to notice here down on the bottom is the number of standard deviations. It's the number of standard deviations from the mean, which by definition we talked about before is actually the z-score. So down here are the z-scores. Right in the middle is going to be where the 50th percentile is, or the middle set of the data resides. At the very far end, we get up to the 100th percent, and on the low end, down to the 0th percent. Now, approximately 68% of the data falls within one standard deviation of the mean. So the mean is always going to sit right here. So the standard mean is right in the middle. That's the average. If we look at here, of one standard deviation from the mean on both sides, this entire area is approximately 68% of the data. Now, if we go 2 standard deviations of the mean, we're going to capture 95% of the data. So in that case, we're now talking, what if we go from here all the way to here, is a total of 95%. And then the last one is if 3 standard deviations from the mean would be from this point all the way over, that's going to be approximately 99.7% of the data, which means there's a little bit of data on both of these tail ends that we're not capturing. Now here's our first example. It's the CDC. So according to them, the heights of the 12-year-old males are approximately normally distributed with a mean of 149 centimeters, a standard deviation of 9 centimeters. And therefore they've given us the shorthand right there. Normal distribution with the mean and standard deviation accordingly. Sketch the distribution, label the mean and the points 1, 2, and 3 standard deviations from the mean. So what we're going to do is just sketch a normal curve, so nice and symmetric like this. And I'll cut it right down the middle. At the middle is the mean, so this is where 149 centimeters reside. And I am going to actually label this, so let's do that right now and put 12-year-old male heights in centimeters. So make sure to label the distribution. Now, if we want to look at one standard deviation from the mean, which means we're talking about the 9 standard deviation, we're going to go over here and we're going to go 1 over and then 1 down. So 149 plus 9 would be 158 for this case right here. And on the low end, we're going to be at 140. That's 1 standard deviation. What if we go a second standard deviation? Let's do 1 more, add another 9, take away another 9. That is going to leave us at 167 on the high end if you add 9, and 131 on the low end. The last one, let's do a third standard deviation, and that's going to bring us to 176 and to 122. Now an example would be if they asked us what percent of students fall within 140 and 158 centimeters in height. If we look at that, we would notice it's 1 standard deviation, and we know 68% of the data sits in there, so it would be 68% of the students. Now let's look at this example with the Major League Baseball players in 2009. The mean of 432 batting averages was .261. So on average, that means when a player went up to bat, 26.1% of the time they actually made it with a hit. The standard deviation on that is 0.034. Suppose the distribution is normal, so they're telling us that with this mean and standard deviation accordingly, and we're going to see that they wrote it here again in the shorthand. Now in part A, they want us to sketch a normal density curve with a distribution of batting averages. Again, label 1, 2, and 3 standard deviations from the mean. So go ahead, if you want to pause the video, sketch your curve, label the mean, and do 3 standard deviations, 2 and 1 standard deviations on both ends. When you do that, what you're going to get is a distribution that looks something like this. Again, don't forget to label the distribution below. Our mean batting average is the 0.261. I'm going to add 0.034 to each deviation on the right and subtract on the left. Okay, part B, what percent of batting averages are above 0.329? Showing your work on here, if we look at the curve, 0.329 is here. They want to know above. So they want to know the area in that little tail. You're going to have to be creative and think about how to do this problem. Now, what we see here is, if this is our mean, we are 2 standard deviations from the mean. So I'm going to go to the right and to the left. So what I know is this area is 95% of the curve. So that's 0.95. Now, I just want this tail end. But remember, this is a perfectly symmetric curve, which means whatever is in this tail end is going to be the same number in this tail end. So the easiest way to really figure this out would be to take the entire graph, which is the whole of 1. So take 1 minus 0.95. And that's going to leave us with the total of these two. Since I just need one tail, let's take this total here and divide it by 2. And if we do that, we're going to get that it's going to be 2.5%. Just think about it logically. There's 5% left over. Cut it in half. We have 2.5 in each tail. On an AP exam, this would be sufficient amount of work to show, but you would need to show something. Continuing on, let's look at this example. We're looking at the batting averages again. They want to know what percent or probability would be the same thing of the batters are between 0.193 and 0.295. So as I look at my curve, 0.193 is there, 0.295 is here. So they want to know this particular area. Now I am going to highlight the fact that the mean of this distribution is right here down at the middle. So ultimately to the right here, we're going to notice that we have the 1 standard deviation. So that's 1 standard deviation to the right. And over here to the left is the 2 standard deviations. So we can think about how we might piece this together. Well, for the 1 standard deviation, I know that 68% of the data is in between 1 standard deviation. But I only want half of it. I want this half of it. So let's just take the 0.68 and divide that by 2. And that's going to give us 0.34. So I know that this first shaded area is 34%. Now to find the other side of it, over here, which is 2 standard deviations, I know that 95% of the curve is 2 standard deviations, but I only want exactly half of it. So let's just take the 0.95 and divide that by 2, which gives us 0.475. And that is going to be this shaded region. So ultimately all we have to do now is add these two values up, and we're going to get 81.5% of the players are in between that range. And we're actually going to skip part D in here. And that's the end of this video.